Now, in the last class, we talked about bonding and electronegativity. Now, we have to draw structures. There's a scientist called Lewis that determined the structures of molecules in organic chemistry, and he used a series of steps, at least 7 steps, to do this. One would ask, what is the shape of water? How comes water is always drawn like this? How? And why is ammonia always drawn with one hydrogen to the back, another one towards you, and another one on the plane? To the back with a broken bond, towards you, shown by the shaded wedge, and on the plane with a regular bond, and there's going to be a lone pair. Why does this look like a pyramid? Why does that look bent? And why does natural gas, methane, have a tetrahedral shape with one hydrogen to the back and another one towards us? So Lewis developed a method of doing this, and he used valence shell electrons, the electrons in the outermost shell of the structure of an atom of an element. And he also applied the octet rule. That helps to explain shapes of molecules. That's like this is bent, that's trigonal pyramidal, and that's tetrahedral. So let's look at what he did. So he used 7 steps. You would want to determine the net total number of valence electrons of all elements in the molecule, like water, and you need to draw the molecule connected with bonds. Any remaining electrons can be put in the central atom if there is any leftovers, and then if there's shortage in the central atom, then you have to donate lone pairs from outside, from the atoms of elements outside the structure, and then you finish by determining the formal charge. But before we do step number 7, let's show how we can draw Lewis structures. For example, of water, Lewis structure of water, ammonia, CH4, and CO2. So let's do those ones. Okay. So what is the Lewis structure of water? So I'm going to follow these steps in your notes. I don't want to flip back to the slide. I'm just generally going to flow down. So step number 1, you want to find the total valence electrons. Total valence electrons. Clean up. Total valence electrons. Okay. So you have 2 hydrogens, you have an oxygen. Now, hydrogen is on the first column of the periodic table, so you'd expect it to have a valency of 1. It's on the first main group column of the periodic table, so you have 2 times 1, and then oxygen is on the 6th main column of the periodic table, so you have 1 oxygen, it's gonna give you the 6 electrons, so the net is 8 electrons. Those are the total electrons, valence electrons, that you have to use to draw your structure to make bonds and lone pairs. Step number 2, at least draw the structure for looking for symmetry. So in fact, you should not show the bonds yet. You have to use electrons to make the bonds. So let me put electrons here to make the bonds. How did I know that hydrogen should be outside? Hydrogen does not take more than 2 electrons, so it has to be outside. Also, halogens don't take more than 2 bonds, so they also have to be outside. Halogens are group 7 elements, the fluorine, chlorine, bromine, iodine. Those ones are always drawn out. Hydrogens and halogens are always drawn outside the structure. Please note that down. Hydrogens and halogens, the fluorine, chlorine, iodide, bromine, must be outside the structure. So I've at least made a bond, and I have symmetry here. So I've used 4 electrons out of the 8. I'm left with 2. So hydrogen is happy because it's happy with 2 electrons. Remember, we said that it only has a 1s, and the s is maximally filled with 2 electrons. So these two hydrogens are happy. The oxygen is not happy. It needs to be an octet. So we have to give it the rest of the 4 electrons that are remaining out of the 8. Now you see you have 4 shared electrons, and you have 2 lone pairs, which makes 8 electrons on oxygen, and it's happy. So next, any 2 electrons that are shared must be drawn as a bond. The ones that are not shared and shared electrons are called lone pairs. So that will be the Lewis structure of water. He did not define the shapes yet. We'll talk about that later on. So that was for water. What about for ammonia? In fact, after this, one would want to determine the formal charge. All these elements will have a formal charge of 0. So no need to show charges. We'll talk about formal charge after these examples. So what about ammonia? NH3. Again, total valence electrons must be determined. So you have a nitrogen, which is in main group 5, so it has valence of 5 electrons. You have 3 hydrogens. The hydrogen is on the first column of the periodic table, so multiple of 3. Then it means I have 8 electrons to spread. Again, I told you by rule, hydrogens must be outside the structure and halogens. Next, you at least make a bond using some of the electrons that you just summed up. Again, all the hydrogens are happy with 2 electrons because, of course, they only have an s orbital, which is filled by 2 electrons. But nitrogen is not happy. It's a sextet. You've used 6, you're left with 2 more. Those 2 are given to nitrogen, and that makes it 8 electrons around the nitrogen. It's an octet and happy. So next, we show the bonds. Any shared electrons, any 2 electrons shared are bonds. So you have 1 lone pair and 3 bonds, and that will be the Lewis structure. He did not define the shapes. We'll talk about shapes later. We'll determine that the shape of ammonia will be trigonal pyramidal based on what we call valence shell electron pair repulsion theory, VSEPR. Don't fret, we'll talk about that. So what about I think let me do CO2. I will skip CH4. Let me do CO2. What about CO2? How do you determine the Lewis structure of CO2? The steps are very, very similar, and this is how you do it. So again, determine the valency. Carbon is in the main group 4 of the periodic table, 4A. And then you have 2 oxygens. That's not a 0, it's an oxygen. Each oxygen gives 6 valent electrons because oxygen is in the main group 6 of the periodic table. Now, if you sum these up, it's 12 plus 4, you get 16 valent electrons. Those are the electrons to be spread on the molecule. So step number 1 is done. Step number 2, at least draw the element showing keeping symmetry. So to have symmetry, I have to put the carbon in between the 2 oxygens. Next, at least make a bond using 2 electrons out of the net total valence electrons. So I've used 4 out of 16, I'm left with 12. So now, out of the 12, oxygen is more electronegative than carbon, meaning oxygen is further to the right than carbon. So I would expect to satisfy the octet rule for oxygen before carbon. So I give this 6 more, I give this 6 more. Now you see we've used the 16 electrons as determined earlier in step 1. Okay, so now carbon is not happy. It only has 4 electrons around it. It needs to be an octet. So to satisfy it, you have to give 4 electrons by sharing from the lone pairs of oxygen. So in that case, I'll have 4 electrons in between the carbon and the oxygen, and I'm gonna have lone pairs left outside on the oxygens. So I'll have these 2 here, these 2 there. So that way, now oxygen has 8 electrons around it. The carbon has 8 electrons around it. Each of the oxygens have 8 electrons around them. So now I'll use the shared pairs of electrons to make a bond. So that will create a double bond, and I show my lone pairs, and that will be the Lewis structure of CO2, carbon 4 oxide, others called carbon dioxide. Okay, so that's how you do Lewis structures. But what happens if you have elements that are charged? Now there's gonna be a problem. So this is what you need to do in that case. But before we do that, let me show you one more case scenario. So what if you are asked to draw the Lewis structure of NH4, for example? Let's follow the same system. So total valence electrons must be determined. So nitrogen gives you 5. You have 4 hydrogens. That gives you 4. So you have, in fact, there should be a plus here. So you have 9 electrons. Okay, I'll explain to you later why there's a plus there, but let's just say you are asked to draw the Lewis structure of NH4 plus. So because there's a positive sign, that means that there's 1 electron lacking. We have to subtract 1 electron because there's a positive charge. When there's a positive charge on the molecule and you're drawing Lewis structures, you need to take 1 electron out. So you have 8 electrons to take care of. This will be the total valence electrons, 8. Next, write the elements in space, looking for symmetry. I told you by rule hydrogens are always outside. Next, at least make a bond using 2 electrons to connect all atoms possible. Let me get rid of this line. Okay. So now my compound, my Lewis structure should be HN. I don't know why my pen keeps doing this. Let's see if I can set it. Okay. So you'll have a bond there. Where you have the 2 electrons shared is a bond. But remember, you still have a plus sign, so we use brackets and put the charge outwards. Now, the question is, why do we have a plus sign there? It's because of formal charge. So whenever you're given a structure like this and you want to determine formal charges after drawing the Lewis structure or during the drawing of Lewis structures, you have to use a formula which is number of valence electrons on free neutral atom, just like it's on the periodic table. Okay, and then you're gonna subtract any lone pairs. So you subtract non-bonding electrons, and then you subtract number of bonds. Alright, now that we know how to draw the Lewis structures, let us see where the plus sign comes from. So let's say you are given NH4 and you want to determine the formal charge. First, what I'll do is at least draw it like this to have a picture of it. I don't know the charge of hydrogen. So to find the charge, I'll use the formal charge equation. Formal charge equals number of valence electrons on free neutral atom minus unshared electrons minus number of bonds. So the formal charge of hydrogen is going to be equal to, applying this formula, hydrogen is on the main group 1 of the periodic table. So the valence is 1. There's no lone pair, so 0. Number of bonds, if I'm focusing on 1 hydrogen, which you should, it's only 1 bond bonded to it. So charge on hydrogen is 0. All these hydrogens have charge of 0. We don't write 0 on them. What of the formal charge on nitrogen? So nitrogen, is on the main group 5 of the periodic table, this one. So it has a valency of 5 when it's neutral. There's no lone pair, but the nitrogen is surrounded by 4 bonds. So I'm giving it an answer of +1. So if you use that format of the formula, or use this or use this, the answer will be the same. I prefer using the first one, so I will not discuss the rest. So that's where the plus sign comes from. Whenever we write NH4, we always put a plus sign on it, because the nitrogen actually in the structure has a plus on it. So what if I would ask you to determine the formal charge of the oxygen to the right? Okay, sorry, I need to draw. Okay, so what if I ask you to find the formal charge of this oxygen? Okay. What if I ask you to find the formal charge of this oxygen to the right? So I'll do the same thing. A formal charge of that oxygen is going to be equal to the valence of oxygen on the periodic table. Obviously, oxygen is in main group 6. So I'll say 6 minus, how many lone pairs shown? I have 6 lone pairs. How many bonds to this oxygen? Number of bonds? 1. So answer is -1. So this one will have -1. In fact, I just write negative. Same applies to this. You do the same thing, it's going to be 6. Valence of the oxygen in the neutral atom is 6. I have 6 electrons, 3 lone pairs, 6 electrons, then I minus 1. So the answer is -1. So this one too has a charge of minus. What about this one on top? For this oxygen, the formal charge will be equal to the valency of that oxygen on the periodic table. It's on the 6th column, 6. How many lone pairs? 2 lone pairs, which means 4 electrons. Then how many bonds? 2 of them. So 6 minus 6 is 0. So this oxygen does not have a charge. What about the formal charge of the carbon? Carbon on the periodic table is on the 4th main group, so it has a valency of 4. How many lone pairs? None. And then how many bonds? 4 around the carbon, 0. The carbon does not have a charge. So actually this one is a carbonate. It's written as CO3, and it's going to have 2 minus. That's where the 2 minus comes from. The 2 oxygens left and right have negative charges. So that's how you do formal charges if asked. Apply any of these formulas, the answer will be the same. Now, oxidation states can be calculated the same way, but now for oxidation state we assign electrons of a bond to the more electronegative atom. So like here, 2 electrons shared, but these electrons are technically given to chlorine. Now if you were to check, chlorine is in group 7 of the periodic table. So if it's on group 7, then it has a valence of 7. So the outermost electrons are 7. How do you make those 7? How do you make that the outermost shell filled up? You are supposed to add 1 electron. So that's the 1 electron there that satisfies the octet rule for chlorine. So there's 1 extra electron. There's 1 extra electron. So the oxidation state of chlorine here is -1. And because hydrogen donated 1 electron to share but is taken away, the oxidation state will be +1. Okay, this one lost, so you need to give it back 1. This one gained an extra electron, so you need to take it out to go back to the valency of 7, so you subtract. So that will be the case with the oxidation state. But with formal charges, you'll have to consider them separately. Hydrogen always has a valency of 1. So here you only have 1 electron, correct? So the formal charge here should be 0. Okay? The formal charge should be 0 because it's normal for hydrogen to have one valent electron. We are splitting the two electrons that make the bond to find the formal charge. It's just another way of doing it. Here, chlorine has 7 electrons. Naturally, chlorine has a valency of 7, so it's comfortable. It's in its natural form of valency, so the formal charge is 0. So each of these have 0 formal charges. But technically, whenever we are talking about electronegativity, we'll say this is partially negative, this is partially positive, because dipole moments will point toward chlorine. The electron density, like we said before, will be mostly towards the chlorine, which is more electronegative. Okay, so now, what do you do if you want to draw the Lewis structure of H3O+? So again, step number 1, determine the total valency. You have 3 hydrogens. Each hydrogen brings a valency of 1. And then you have 1 oxygen. Each oxygen has a valency of 6 because oxygen is found in main group 6. And then you have a plus charge. I told you whenever you have a positive charge, what you need to do is to subtract 1 electron, because to get the positive charge, you have to lose 1 electron. So you have 8 valent electrons. So the next step is to draw the elements in space. Remember, I told you hydrogens and halogens must be out. Next step is to at least make a bond. Okay, at least make a bond, which is what I've done. You realize that I've used 6, I had 8, so 2 more. I give it to oxygen to satisfy the octet rule. Hydrogen is fine with 2 electrons. Next is make bonds. I really draw lines to show the bonds using the shared electrons. But now we are not done. We have to find the formal charges. Obviously, if you do the formal charge of hydrogen, it turns out that the formal charge of hydrogen will be 0. Hydrogen has a valency of 1 in the periodic table. It's on the first main group element, or main group column, the periodic table. There's no lone pairs on these hydrogens, so minus 0. And then each of the hydrogen, considering one of them, is bonded to 1 bond, so you get 0. What about the formal charge for oxygen? Okay, this is step 7, I think 6, 7, whatever it is on Lewis structures, drawing of Lewis structures. So the oxygen is in main group 6 of the periodic table again. It's right there, so it has a valency of 6. So I write 6. Do we have lone pair? Yes, the lone pair has 2 electrons, so I put 2 electrons. How many bonds do the oxygens? I have 3 bonds. Okay, so I have 6 minus 5. The answer turns out not to be 1, but plus 1, because you are considering charges. That's where this positive comes from. So the Lewis structure of H3O plus, going to step number 5, will be drawn like that. Alternatively, one will draw it like this, and then externally put the plus charge outside the brackets. Okay. So you do the same process for this compound. So step number 1, find the total valence electrons. Okay, let's see where this guy comes from. Where does that come from? It must be group 5 or what? Let's see. Yeah, it's in group 5. It's arsenic. So the valency is 5. So you have 3 oxygens. Each oxygen brings 6 electrons, and then you have 3 negative charges, so you have to add them, because that means you have 3 extra electrons. So remember, arsenic brings 5 electrons. You have 3 oxygens, so it's 3 times 6, and then you have 3 negative charges, so it's 3 3 negatives, which means it's 3 electrons. So if you sum all this up, 18 plus 3 is 21 plus 5 is 26 valent electrons. So next, from that step number 2, that was step number 1. Step number 2 is at least write them in symmetry. So the only way I can have symmetry in the drawing of the elements in space is to put AS in the middle so that the oxygen can be spread apart outside. Now I have symmetry. And then step number 3 is to at least make a bond using 2 electrons. Okay, so between oxygen and arsenic, who is more electronegative? Remember we said electronegativity increases generally across and upwards. So oxygen has to be more electronegative than arsenic. So we have to satisfy the octet rule for the oxygens by adding 6 more to make 8 electrons. And then after that, inspect and count how many electrons have we used. 8, 8, 8. So it's 24. We are left with 2 electrons out of 26. I give that to arsenic. So now everyone is octet and happy. 8 electrons on oxygen, oxygen, 8 on the arsenic. You see there are 8. If I circle this, there are 8. And then 8 on this oxygen. So everyone is happy. So we need to find the formal charge. Let's start with the AS. So to find the formal charge of AS, it's in main group 5, so it's 5 minus. Do you have a lone pair? Yes, 2. And then how many bonds? Oh, I forgot to do the bonds. Let's do the bonds and see. So it has 3 bonds. So it's 0. So AS has no charge. What about any of these oxygens? Once we determine the charge of one should apply to the other ones because they are similar. So the formal charge of the oxygen, for example, this oxygen to the right, is going to be 6. Oxygen is found in the main group 6. Valency of, this is the valency of oxygen, valence electrons in oxygen, free neutral atom of an oxygen. So it's 6 minus, how many lone pairs? 3 lone pairs, which means 6 electrons. How many bonds? 1 to this oxygen. So I get -1. So each of these oxygen must have a charge of minus, and that's how this structure was found. Okay. So the process goes on and on and on and on. So what about this one? I would first of all find the total valency. Carbon has a valency of 4. You have 2 hydrogens, that will give you a multiple of 2 by 1. So I have 6, and then I have oxygen, which gives me 6 valent electrons. So total is 12, and that's what's done here. So I have 12 valent electrons to spread around. Step number 2 is to find symmetry. Now, oxygen, by rule, tends to bond to 2 bonds only. So I don't want to put oxygen in the middle. Instead, I'm going to put carbon. Let me erase. So let me repeat. There are 2 representations here. So you'd either do this or do this. You don't want to do this because this will take more than 2 bonds, and that means oxygen will have a charge. One of the rules for Lewis structure is to minimize charges. So instead I'll take this because now oxygen can be outside. Hydrogen is outside by rule. So next, step number 3, carbon can take up to 4 bonds. Oxygen naturally love to take only 2. So that's why I'm taking this structure and not that. So next, we at least make a bond. I have used 6 out of the 12. So now hydrogen is happy, carbon is not, oxygen is not. Oxygen is more electronegative than carbon. So we first satisfy the octet state for oxygen because it wants the electrons. It has high affinity for electrons than the carbon. And count. So we have used 12. But now there's no more electrons to give to carbon to make it an octet. So we have to share. So in that case, step number 5, you'll be left with 2 lone pairs. 2 are shared here. You get that structure. So if you're to show bonds, that's what you end up with. This will be the Lewis structure of CH2, which happens to be an organic molecule called formaldehyde. Okay, so you can make multiple bonds by doing extra sharing. Carbon monoxide. Step number 1, valency of carbon is 4, valency of oxygen is 6. I have 10 valent electrons to share. Step number 2, draw them in space. Step number 3, at least make a bond. Step number 4, add more electrons. We've used 2 out of 10. Oxygen is more electronegative than carbon. Satisfy the oxygen octet first before you satisfy the carbon. So 8, 9, 10. Okay, next, carbon is not octet, oxygen is, so we have to donate. So you get, now carbon will have 6 electrons around it. The oxygen still keeps its 8 electrons. Carbon is still not happy, so we do one more sharing of a lone pair. We do one more sharing of a lone pair. So that takes us here. So you have 6 shared electrons, and then the oxygen will be left with just a lone pair outside. Okay, so let me clean up so you don't think this is an electron. So this will be the structure, and then to show bonds, you end up with that structure. Formal charges. Formal charge of the carbon in CO. The carbon has a valency of 4 in the periodic table. It's on main group 4. There's 1 lone pair, which means 2 electrons, and there are 3 bonds, so I put 3. You get -1. That's where this -1 came from. Formal charge of the oxygen. Oxygen is in main group 6 of the periodic table, valency of 6. There's 1 lone pair after drawing the Lewis structure, which means 2 electrons, and then there's 3 bonds. 6 minus 5 plus 1. That's where this +1 came from, and this will be the correct Lewis structures after taking care of formal charges. Okay, next we'll talk about resonance in the next recorded video.